To build our green energy future, we are undertaking some of the biggest infrastructure projects in human history. But here's the thing, a huge part of this new world is being built completely out of sight, right on the bottom of the ocean. So let's dive into this massive, hidden grid that's connecting us to clean power. So what kind of power are we really talking about? Well, it all boils down to this number, 2 gigawatts. Now, to give you a sense of scale, a single gigawatt can power about 750,000 homes. So we're talking about an absolutely incredible amount of energy, enough to power a whole city. And here's the really wild part. This isn't the total output from a bunch of different power plants. Nope, this is the capacity of a single offshore connection system. It's basically a standardized plug-and-play setup that's designed to be rolled out at a massive scale. Which, of course, brings us to the big question here. Building this future means laying thousands of kilometers of high-tech cable through some of the most dynamic, most sensitive marine environments on the entire planet. So, what are the trade-offs? All right, first, let's look at what's driving this incredible engineering feat. Why this urgent push for a 2-gigawatt standard? Well, as the European grid operator TenneT says, offshore wind is absolutely central to hitting climate goals. It's just not optional. The real challenge is getting all that power from the wind farms, which are being built further and further out to sea, back to the mainland where people actually need it. And they are on a serious deadline. To hit these 2030 and 2050 targets, the pace of connecting all this offshore power has to literally quadruple. We have to go from connecting 1 gigawatt a year to 4. You just can't do that with custom one-off projects. You need an assembly line, and that means a bigger, standardized system. Now, the tech that makes all this possible is called high voltage direct current, or HVDC. The best way to think of it is as a superhighway for electricity. See, the standard AC power in our walls loses way too much energy over long distances. HVDC is just far more efficient, which makes it the only real choice for moving this much power from so far offshore. But as we're about to see, how you design that HVDC system, well, that turns out to be absolutely critical. So that's the blueprint that's getting rolled out in Europe. Now let's fly to the other side of the world to see how this actually plays out in a real-world environment with one of the most ambitious energy projects ever dreamed up. Let me introduce you to the Asian Renewable Energy Hub. This is a massive project proposed for the remote coast of Western Australia. The idea is to use wind and solar to power local industries, and then, using subsea HVDC cables, export green energy all the way to Southeast Asia. I mean, in terms of sheer capacity, this thing is second only to the Three Gorges Dam. It's huge. And this right here, this single slide, tells the whole story. On one hand, you've got the clean, elegant engineering concept, and on the other, you have the messy reality of where you have to build it. The wild, churning, and incredibly important waters off of 80 Mile Beach. So let's zoom in on that place, 80 Mile Beach. Because if you want to understand the risks of a project like this, you have to first understand the incredible natural forces that are at play there. First of all, the weather is just intense. This region gets hit with more tropical cyclones than any other part of Australia. So any infrastructure you build has to be tough enough to survive some of the most powerful storms on Earth. And then there's the water itself. The tidal range here is just staggering. We're talking a maximum difference between high and low tide of over 10 meters. That's more than 30 feet. This creates these incredibly powerful currents that are just constantly churning up the seabed, which is why the water is always so murky and full of sediment. And yet, this incredibly challenging environment is also a world-class sanctuary for wildlife. The 80 Mile Beach Marine Park is a critical habitat for endangered sea turtles, it's a highway for migrating humpback whales, and it's home to vulnerable species like the green sawfish. For millions of migratory shorebirds, these mudflats are like a vital gas station on their epic annual journey. And it is so important to recognize that this is not an empty wilderness. This is sea country. It holds deep cultural and spiritual significance for the traditional owners who have lived on and managed this land and sea for thousands of years. Their connection is a vital, living part of this story. Okay, so given this unbelievably complex and precious environment, what are the actual risks that the official environmental impact assessment brought to light? Let's break them down. So the official assessment looks at 5 main areas, but for this project, the really big concerns fall under sea and people. Things like the marine habitats, the water quality, the animals, and of course, the cultural heritage of the area. During the actual construction, the risks are very direct and physical. You're literally digging trenches in the seabed, which kicks up all that sediment that can smother nearby habitats. You've got the constant risk of fuel spills from all the ships, intense underwater noise that can disorient whales and other animals, and even the threat of invasive species hitching a ride on the hulls of the construction vessel. And these risks don't just vanish when the construction crews leave. For the next 50 years, these cables will be sitting on the seafloor, generating heat and electromagnetic fields. There's also the long-term risk that a cable could break down and release contaminants, and just their physical presence could block access for traditional fishing and other cultural activities. So, this is where the story takes a turn. We've laid out the environmental challenge. Now let's look at how the specific engineering choices, the ones from that 2-gigawatt blueprint, are actually designed to act as a shield against these exact risks. Okay, this is the crucial part. Not all HVDC systems are created equal. A simpler system called monopolar actually uses the seawater itself to complete the electrical circuit. This creates a direct electric field in the water that can seriously disorient animals like sharks and rays, which use natural electric fields to hunt and navigate. But the system being proposed here is bipolar with a metallic return. It's a closed loop. The current is contained within a second cable. This creates a much smaller, contained magnetic field instead. It is a very deliberate engineering choice made to protect the unique marine life here. So, the strategy to protect the environment is really a 1-2 punch. First, and most importantly, you choose the right cable technology, that bipolar system, to minimize the impact from the very start. Then, step 2, you bury that cable deep enough into the seabed. That reduces any leftover magnetic field and heat, effectively shielding the marine life from the cable's effects for decades. And that brings us right back to where we started. That 2-gigawatt standard isn't just about raw power and efficiency. It's also about embedding solutions to these really complex environmental problems right into the basic engineering design. But it still leaves us with this fundamental question. Even with the absolute best technology and the smartest mitigation plans, projects on this scale will always have an impact. There is simply no such thing as a consequence-free megaproject. So as we design this clean energy future, we have to keep asking ourselves, what is the true cost? And what are we as a society willing to pay for it?